Hello everyone, is the Prophet Michael David, aka Aries, and today is going to be kind of a filler video. My last video on the first day of Passover was pretty deep, and I might want to do one on the last day of Passover, which is in a couple more days. But I did want to keep consistent on my videos, so I decided to make one today, uh, talk about a couple memes that I really like, and then show you guys how I'm progressing on my Riemann work. Okay, because of retention, and I'm slowly learning about this stuff, we're just gonna do the memes first. Plus, they're funny, and there's only three memes. So here's the first meme. All right, I think the first time I saw this meme was I was watching a Dr. Becky meme review YouTube video, and I just totally started cracking up because it's so true. Physics, people consider physics as being so boring and dry and everything, but astrophysics, especially with all the pictures of like James Webb these days and everything, people are utterly fascinated by it, including myself. But yeah, it's one of those, it's so true, it's hilarious memes. All right, I actually just found that one today and it's so hilarious. I mean, I know the basics on like Einstein condensate and time crystals and stuff like that, but just between the look on the dragon's face and the I like crystals, and it kind of like mimics the meme about the kid, the zombie kid that was like I like turtles. It's just, especially the face on the dragon is just hilarious. All right, and now for the last meme, I'm going to do a little intro and build up because this is like one of the greatest memes I've ever seen in my life. Recently, I was watching a YouTube channel. They were doing an interview with Grant Sanderson, who's the Three Blue One Brown Guy YouTube channel. If any of you've watched that, and again, he was doing a meme review of some math memes, and this one came on, and I literally almost peed my pants. Everyone's a gangster until you invert. It's so funny. It's so funny to me. And just the look on the cat's face in the bottom part of the joke when he's being swallowed by the fish. Dude, I'm still giggling about it. Like I said, it's one of the greatest memes that I've ever seen in my life. All right, that concludes the meme part of this video. So what I'm going to do now is show you guys my Riemann work. It's all called Chasing Riemann, or one variation or another. And if you want more information, definitely watch my Chasing Riemann video. That's a couple of videos ago. But I'm going to show you what I've been doing and show you some updated graphs at the end and try to explain the situation. So I'm not going to totally redo the whole thing from start. Um, like I said, watch my Chasing Riemann video if you want to see that. I'm just going to give a brief synopsis of the strategy that I'm using, and we'll go from there. All right, so here's the short synopsis from the last Riemann video. That is the equation that was discovered by Geoffrey Ligarius in 2004 that I found that is equivalent to solving the Riemann hypothesis. But I looked at it and I'm like, you don't need to use imaginary numbers to solve the Riemann hypothesis. This is the only proper way to do it. So that's how I attack the problem. You can look up the terms if you need more help, but basically Hn is the nth harmonic, E is Euler's number, Ln is the natural log, and that sigma n, that's the sum of all divisors. You can get that number by a sum of all divisors calculator that you can find on the internet. That's what I use. Okay, that's a related equation by a guy named Robin or Robin, and has some of the same symbols, except for that e to that gamma. What that gamma is called Euler's constant. We're going to get to that very shortly, but that's what it is. And that is another related equation by a guy named Gronwell, which shows another relationship between n log of n, which is ln really. I don't know why they write it that way. Um, Euler's constant, and then the sum of all divisors as well. So, and that point is from a guy named Kaneko, who must have worked with Geoffrey Ligarius on his paper that showed that once up to a certain point, up to over n equals 60, you don't even need the plus hn on Lagrange's equation, that e up to the nth harmonic times the natural log of the nth harmonic is enough to always be greater than the sum of all divisors of n. And that is a screenshot of my spreadsheet that only confirms this relation. I even highlighted the columns for you so it'd make it easier. The two yellow columns are the harmonic ones, the transcendental ones. Those are the ones that should always be more than the teal colored one, which is the sum of all divisors. And you can tell the one with the plus hn in it, the right-hand yellow column, that is always, it's equal at 1, but every other number from 2 to infinity, it's always greater than, or that's their conjecture. But you can see the other one without the plus hn, that one is also larger than the sum of divisors from 120 onwards. Now, up to this point, that is how I've been generating those lines. I mean, I color them and everything. But as I told you guys before, I'm just basically taking the sum of divisors of the entire line, which go up and down, they ebb and flow, and I'm just cutting off the very tippy tops of the waveform. And you think it would be random, but it's not. And we'll get into that here in a little bit. But as you can see, to do that, I basically am taking spreadsheets of every 50,000 numbers, every 50,000 harmonics, and then I'm just cherry picking out the ones that are the maximums. But the numbers are getting up pretty big. The number, that one is 700,000 to 750,000 because the last number that I needed was 720, 720, 720, 720, 720, 720, 720,720. But the next one is going to be like 1.4 million. And the numbers keep going up so fast that if I did it this way over and over, only 50,000 numbers at a time, it's going to take me forever to get to the next numbers. I mean, I'm going to be working for weeks and then months just to get the next number. So I have to come up with a different way to estimate the harmonics instead of doing spreadsheets to calculate them perfectly. Now, there is no current way to perfectly calculate the harmonics, only to estimate them. And that equation right there is called Euler's constant, or that constant right there. You know, holy cow, Leonard Euler again, what a surprise. And it's super famous, but you can use that constant to generate very good approximation of the harmonics. And I've heard about it before, but I didn't really, and again, its notation is gamma, but I hadn't really looked into it or really thought of any way to try to use it. Like I said, I've heard about it before. I've definitely been to the wiki page. So I really wasn't going to use it, or didn't really plan on using his constant at all. But then in the course of my work, it just popped out of my own work. And you could say that I independently rediscovered it, or a different way to produce it that's much actually easier than using that limit. And here's how I did it. So that was another spreadsheet that I made to analyze the harmonic series. And if you look at the green column and the blue column, I noticed that both of those columns of numbers were converging toward a value that was in between the two of them that was roughly 1.781724. Here's my OG sticky. And so it kind of looked familiar. And so I took the natural log of it, and that's the gold column, and that's Euler's number, or Euler's constant. But here's the graphs of the green and the blue that I graphed out that show that they do converge to the same thing. So I saw that graph, and I was like, wow, I mean, the blue one converges pretty fast, but that green one converges really fast. And so I took the natural log of the green one to see how well it fit actually Euler's constant, and here's the graph of that one. As you can see, that converges real fast. Now, even that black line is I manually typed in like the first dozen, 15 digits of Euler's constant straight from Wiki. And so that's what that line is. And as you can see, like it's dead on that line. So now that I have a different way to calculate Euler's constant, and I can see that it converges so quickly that it's going to be consistent through almost the entire number line, um, I can use that constant to uh, very well estimate even larger and larger of those colossally abundant numbers, the maximums and everything. And again, I have to do that because of this. All right, so that's the bottom of my current Chasing Riemann 4, like my maximum spreadsheets. And as, like I said, right now it ends at 720,720. But the next number is going to be like 1.4 million. So to find that number the old way with my old harmonic spreadsheet, I got to make like 15 more spreadsheets just to get one more number. And then the one after that, it's even more and more and more and more, which is why I need to estimate it. And that's because while that number seems big, uh, it is not nearly even close to as big as my numbers on my other spreadsheet. And you might be asking, like, where are you getting these numbers in the first place? How do you know they're maximals? And that's because of the other spreadsheet I showed you that I'll show you right now, just to show you how fast these numbers are going up. All right, that is the start of my Chasing Riemann 3 spreadsheet, that's how I'm finding the maximals. And they're all on mod lines, but the mod lines keep getting longer and longer. And we've had this discussion many, many times before, but A mod B, all it is A is where you start, and B is the spacing between your numbers. And so you can see on the left of my graph, I changed it from like only a true geometer would call the natural numbers or the set of natural numbers the 1 mod 1 line, but I do. So you start with the 1 mod 1 line, start at 1, add 1, 2, add 1, 3, all natural numbers until you find the pattern, which is 2, and then you go to the 2 mod 2 line, and then you can see you find the pattern on that is 3, so it turns into the 6 mod 6 line, and the pattern keeps going up, up and up and up and up. The numbers get higher really, really fast. And like I said, those purple dots, I made those purple because those are both starts and ends of mod chains. You can think of this whole thing as, mod chains that are tied together that are getting bigger and bigger. One mod chain to a 2 mod 2 chain to a 6 mod 6 chain to a 12 mod 12 chain, and they keep getting bigger and bigger. How much bigger? This is how much bigger. And that is currently the end of my spreadsheet, or as big of numbers as I've gotten to. And they're starting to get astronomically large, which is a problem since I have to do all those sum of divisors by hand or and at some point I'm going to reach a processing limit. But you guys can look through it. But the mod line with all the 17, and remember, that's the spacing. The primes naturally pop out of this. Is just an analysis of the most divisible numbers in the number line. It had nothing to do with primes, but the primes pop out of it naturally. But that mod line that is right next to the 17 is 10,810,800 mod 10,810,800. But the next mod line it's going to create, and that's basically going to be 19 guaranteed, is 183,783,600 mod 183,783,600. So why are the primes, or numbers that are factors of primes, which is everything, but why are the primes popping out of this analysis? It's because it's creating this. I've showed that screenshot a bunch too. That's the colossally abundant numbers from Jeffrey Lagaris's paper. And what my numbers on the spreadsheet are is the green ones are that graph, or yeah, whatever you want to call it. Those are the green numbers in my spreadsheet. The blue numbers are the ones that are in between the green numbers, but are still maximal highs. So I don't know how mathematicians collected those numbers on that graph, but I did them all manually, and all my numbers are local highs of the sum of all divisors. Just the green ones are those numbers, and the blue ones are the ones I found myself that are in between the green numbers. All right, so lastly, what I'm going to do now, and obviously I'll make another video about it, is I want to keep developing my spreadsheet and my graphs with even larger and larger numbers. But to do that, I'm going to have to use Euler's constant, and I'm just going to use the value straight from Wiki. And with that, I'm going to make very large but very good approximations of those equations, and then I'm going to set that against the actual sum of divisors to see that it is going to always be over it. But then I'm going to use that to develop my spreadsheet and those 5 graphs. And by the 5 graphs, I mean the 5 graphs that I showed you in my Riemann goes down video. And right after this, I'm going to show you them again because I've developed them more. I've added in more numbers. And then in the next video, I'll just show you more. So these next 5 are what the 5 graphs look like from 1 to 720,720. All right, that's about it for today. Video's longer than I thought, but still pretty good overall. I don't know when my next video is going to be. It might be on the last day of Passover, but I'm trying to do videos pretty consistent, even if they're not earth-shattering, just to keep informed and not have any huge gaps. So I'm trying to do about 2 videos a week. That's been about my average for the last year. So signing off. As always, rule number 1, do not touch other people without their consent, aka do not hurt each other. And rule number 2, it's all about honesty. Lies are ticked down, aka try not to lie. All right, y'all have a good day. I'll talk to you later.